So let's take a look, how do these giant black holes and active nuclei form, and how does that relate to galaxy formation itself? So first thing that people started studying when quasars were recognized as an interesting phenomenon in their own right, and you probably know that this was done here at Caltech by Martin Schmidt in 1963. They recognized what quasars were. They found out that there were many more quasars at higher redshifts than there are here now. In fact, it's like an exponential growth. And you can't just look at any individual objects, so there's a whole distribution. The easiest thing to describe it is luminosity function, distribution of luminosities of objects. That turns out to be power law. And so at low redshifts, you have power law distribution of luminosities. At high redshifts, you also have power law distribution of luminosities, and it's shifted. Now, you don't know, is it shifted up and down, meaning same number of objects, same luminosities but more objects, or left and right, same number of objects but they used to be more luminous. And so those two are called density evolution or luminosity evolution. And insofar as the luminosity functions are power laws, there is no way of telling. Fortunately, it's not pure power law. If you look at low enough luminosities, you see that there is a bend. So there is a knee to this luminosity function of quasars. And when you then look how that behaves as a function of cosmic time, you find out that there is both luminosity and density evolution, or rather there is luminosity-dependent density evolution. But thanks to the deep surveys, now we have pretty good understanding how that goes throughout the history of the universe. And the numbers evolve in time. Interestingly enough, as you look from here back in the past, you see more and more quasars. And the numbers peak around redshifts of 2 or so, plus or minus 1. And then they decline again at high redshifts. And this is just like history, cosmic history of star formation. And for the same reasons. The same processes that build up galaxies, which is dissipative merging that then causes star formation, are the processes that feed black holes and therefore increase their mass. And so at first you have nothing. You start building them up more and more. Galaxies keep merging. That process culminates a couple of gigayears, few gigayears after Big Bang, and then slows down and declines, just like star formation history in galaxies. So star formation history of galaxies and history of supermassive black holes or active nuclei kind of track each other. And moreover, there is some real energy exchange too. Now, not only do the galaxy merges affect what's going to happen with an active nucleus, but also the other way around. Because these things put a lot of energy out, both through electromagnetic radiation, so they could drive like stellar wind equivalent from an active nucleus, and also mechanically with these relativistic jets. So that's now called feedback. And this is again a picture of Centaurus A galaxy with the radio map superposed. And the amount of mechanical energy that's pushed out through radio jets in the radio lobes is of the order of 10 to the 6 terax. And that's similar thing as total amount of radiation that emits over periods of tens of millions of years. And that is comparable to or even larger than the binding energy of that entire galaxy. So if you couple 100% of energy output of an active nucleus, it will just blow the whole galaxy apart. It doesn't do that because it doesn't couple perfectly. But even if a small fraction of it gets coupled to the, say, interstellar medium, that can clearly affect the accretion rate because it'll start pushing out the gas that normally would accrete in a black hole. And so they will kind of go in a feedback cycle like that, and that may be why we see correlations between black hole mass and the all-stellar mass in galaxies today. So there is this whole coevolution of galaxies and their supermassive black holes. They're all assembled through mergers. Mergers stimulate star formation, feed the AGN. AGN stop the process, then more merging happens, and so on. And people like Phil Hopkins here are studying this kind of stuff and explaining how the joint evolution of quasars and their supermassive black hole goes. But then the question remains, like, how did it all start? So you have hundreds of millions or maybe billion solar mass black holes already at redshift 5 or 6 when the universe was a billion years old. And where do they come from? And there are several different possibilities. First, you can say, well, there's some small black holes came out of the Big Bang for God knows what reason. That's pretty ad hoc, but it's not impossible. And then they can serve as seeds onto which you grow more and more stuff. So there are good reasons why this can't be right. The natural thing is that you have supermassive stars, population 3 stars exploding, leaving black hole remnants of few solar masses. Then those keep gobbling up stuff and growing and growing and growing. Remember, mass accretion starts and goes at an Eddington rate, it grows exponentially. Another possibility is you make a really dense star cluster. We see star clusters forming in star-forming regions. Well, star cluster can undergo gravitational collapse and make a black hole. Or maybe you don't need to make stars at all. All you need is sufficiently dense core, which could be a combination of dark matter and visible stuff that goes over the critical limit and makes a black hole. So whichever way it works, it has to work very efficiently to build up quasars that we see. And so there are now simulations of how that could be happening, making stellar black holes, then ever bigger ones and bigger. And someday we'll probably see gravitational wave signals of the original buildup. There are also simulations that say, well, just start with a mixture of gas and dark matter, and under certain conditions, you can dissipate enough energy that you can just collapse the thing directly. And that also works. So in terms of how do you grow black holes, just like galaxies merge from smaller pieces into ever bigger ones, black holes will be assembled in the same fashion. There'll be black holes in individual galaxies that merge together and so on, so you build ever bigger ones. So there's a merger tree like this. And we actually see this happening in close binary active nuclei. Here are pictures of some. The one on the left is a radio map, and you can kind of see there are two radio sources with jets, and they're spiraling in together. The one on the right is X-ray image from Chandra to quasar-like nuclei in an elliptical galaxy nearby. And we've seen lots and lots of binary galactic nuclei, but because of the limitations of resolution, we see them usually kiloparsecs or 100 kiloparsec separations. These will take many millions of years to merge. And the cool thing will be to find those that are so close they're going to merge in our lifetime. Well, that's one of the targets that is anticipated for gravitational wave observatories like LIGO, or someday LISA, and people like our theoretical relativist group here are doing simulations of merging black holes and all the signatures that can lead for observatories like LIGO to see. The interesting question then is it just gravitational waves, or is there also some electromagnetic signal that accompanies this merger that we can detect with optical telescopes? And right now this is somewhat unclear.